Well, we've had so much practice recently proving that sequences converge to various things, if they are sums of sequences or products of sequences or from various algebraic formulas, that you might be starting to get the impression that a sequence always converges, and it just takes the cleverness to prove it. But of course, that can't be right because plenty of sequences don't converge. And math is not just about proving the positive things, we also have to be able to prove the negative things, the unfortunate side effects of the way things work. So let's look at this sequence, -1 to the n, and what we're going to prove right now is that this sequence doesn't converge. So let's have a look at this sequence. This is the sequence -1 to the nth power. Now, as n goes through the positive integers, then this alternates between being -1 to the even, which is +1, and -1 to the odd, which is -1. And so here's a table of values for our functions. For our function, when n is 1 or 2 or 3 or 4, it alternates between -1, 1, -1, 1, -1, 1. These numbers don't settle down to any particular value. They don't get closer and closer to any particular value. Half of them remain very remarkably close to 1, and the other half of them remain very, very close to -1, but they don't, as a collection, settle down to any value, and so they don't have a limit. But that requires some proof. And so what we're going to do right now is we're going to prove that this sequence does not converge, that the limit does not exist. So how are we going to prove that? Well, you already know how to prove that. You have the definition of a limit. It's this logical form. We know how to negate it, so we're going to negate this definition, and then we're just going to follow our nose in terms of what that means about our proof. So let's recall the definition. The limit, if it were to exist, would be the value L, such that for every epsilon greater than 0, there exists an n, such for all in the naturals. If n is going to be beyond cap n, then this distance is less than epsilon. And this is the challenge with this sequence. It's hard to pick out an L so that this distance between the terms an and L will always be less than some value epsilon. If epsilon is a small number, we can't get them all close to L, and that's why it's not going to converge. So how are we going to construct a proof of that fact? Well, the first challenge is when we're trying to prove that a sequence converges, we're usually trying to show that it converges to something in particular, and we have an L in mind to which it converges. And then we go on and say, okay, let epsilon be positive. But here, we're trying to show that it doesn't converge. We're not trying to show that it doesn't converge to 0, that it doesn't converge to 1/2, that it doesn't converge to 2. We're trying to show that it doesn't converge to anything. And if we're trying to show that, then basically we need to say, we need to prove generically that it doesn't converge to any conceivable value L. And so what we're going to do here is we're going to show that no matter what value of L you have in mind, it doesn't converge to L. So I'm going to say let L be a real number, and we're going to prove that it doesn't converge to that. Okay. So I don't know what L is. It could be pi. Maybe we're proving that it doesn't converge to pi. It could be 0, which is kind of a natural guess. These numbers sort of feel like they're on average 0. Maybe L is 0. Maybe L is 1 because half of them are 1. The point is we're not going to commit to what L is. We're going to pick out an L generically, and we're going to prove that the sequence doesn't converge to that. So let's write this down. We'll prove that the limit as n goes to infinity of an is not L. Okay, and since L is generic here, then we'll have effectively proven that it doesn't converge to anything. So that's the plan. Now here, what we're going to so what do we know about this L, or what are we trying to prove about this L rather? If L is the limit, then this logic is going to be true. If L is not the limit, then this logic is going to be false. And so let's state in a simple way what it means to negate this statement. So I'm going to take this statement for all epsilon there exists in n, and we're going to negate it. Now, there's a sort of a silly way and an interesting way to do that. So I'm going to take the statement for every epsilon greater than 0, there exists a cap n, such that for every n in the naturals, if n is greater than cap n, then absolute an minus L is less than epsilon. So we're going to take that statement, and then we're going to negate it. So let me indicate that this is what we're trying to prove, because we're trying to show that that's not true. So let's call this the goal. The goal is to show not that. Okay, so that's one way to negate the logic of a statement. We're going to show not that. And this little turnstile symbol just means, well, that's not a turnstile. This is just a little negation symbol. This means that's not true. So we're trying to show that that's not true of the number L, where L is this generic number. Okay, notice there is an L in this statement, right? We're trying to show that that's not true about L. Well, okay, that's kind of interesting, but that's not really as much as we need here. What we need to do is we need to negate all of these, I mean, fully negate this statement so we know what we're talking about. We need to push the negative inside in order to really understand what this is about. And this might seem hard, but I just want you to remember your set theory and logic. When you're negating statements, each of these statements has something that you do when you're negating it. When you negate a universal statement, you get an existential statement. If the negative of saying for all epsilon greater than 0 is to say that there is an epsilon greater than 0 for which it's not true. So when we push this not across the for all, it becomes that there exists. And then similarly, when you negate an existential statement, there is a something, then you get a universal statement. Everything is not that, okay? So we're going to push this not across, and we're going to move it all the way to the inside while reversing the type of every quantifier. So let's do that next, and then we'll see what happens. So this means there exists an epsilon greater than 0. So that'll get the not past there. And then for every cap n, that'll get the not past to there. There exists a little n in the naturals. And then that'll get the not all the way to the inside. And now I'm still not quite going to do everything right. I'm going to say does not imply. Okay? So basically what I've done is I've pushed the not past the universal, past the existential, past the universal, and into the center, which is predominantly an implication. A implies B. Well, P implies Q. And then I'm just going to say P does not imply Q. And that's what happens when we get the not all the way on the inside. And notice that all of these have switched, that all the quantifiers have turned upside down. Now, here I've got a negative implication, which is kind of a weird way of phrasing things. How do we deal with a negative implication? Well, there's only one way an implication can be false in mathematics anyway. So if let's use true and false, T and F instead of 0 and 1. So if you look at the truth table for the implication, it's false only here, and it's true here, and it's true here, and it's true here. And so there's only one way an implication can be false, and that is if the front of it is true and if the consequent is going to be false. That's the only way an implication can be false. And so when we negate this implication, the best way to negate it is to assert that this is true and that is false. So I'm going to rewrite this so that it's an assertion that this is true and that is false. So I'm trying to negate the entire logical statement. And so, oops, I did that wrong. So I'm going to recopy everything here. So there exists a little n so that n is indeed greater than cap n, and so P is true, and this is false. Now this is a less than symbol, so the simplest way to make it false is to change it to a greater than or equal to symbol. And now this basically asserts that the sequence is capable of being far from every number. So let's try to read this. No matter what proximity you're interested in, measured by epsilon, there is a point in the sequence. So, and no matter how far out you read in the sequence, then there is a sequence term beyond that point. So, well, there is a sequence term, and that sequence point is beyond that threshold point. And that sequence term is going to be far from L, right? The distance between AN and L is actually greater than epsilon, so that sequence term is far. So in other words, when you read out, no matter what proximity you're interested in, there's a place where you can, and no matter how far you read out in the sequence, then there's a place beyond that in the sequence where that sequence term is pretty far from L. And you can see that's actually pretty believable given the sequence, because no matter how close you want to get to any number L, like eventually you're either going to still have minus ones or you're going to still have ones, and one of those is going to be like reasonably far from the value L. And so this is the statement that we want to try to prove. Now, so what we've done here is just some simple logical calculation. We've taken the definition of convergence and we've said, okay, we're going to prove that it doesn't converge to L. And then we've negated the definition of convergence and ended up with this statement. And this will become the statement to prove next. So how are we going to prove that? Well, even if you've never proven a statement like this before, even if this is the first time you've seen the negative of a sequence convergence proof, you should know what to do, at least structurally, you should know how this proof has to begin. Because the thing that we're trying to prove says there exists an epsilon greater than 0. And so, there's really only one way this thing could begin, and that is we have to begin with the choice of the epsilon. So if you're trying to illustrate existence, then the natural way to illustrate existence is to choose. And we can't just choose any old epsilon. I can't choose epsilon to be 0, for example, because it needs to be a number greater than 0. Now, I don't know how to choose epsilon, and I could leave this blank and just carry on with the proof, or I could take a good guess and then try to carry on with the proof, and maybe if I'm wrong, I could come back later and change it. Epsilon is the sort of the proximity that you cannot really succeed at. Now, we could take a guess at what epsilon might be here. We've got sequence terms -1 and 1 and -1 and 1 and -1 and 1. And there seems to be like a general distance here of straying to up from where you were, to down from where you were, to up from where you were, to down from where you were. And so there's like these sequence terms are going up to, down to, up to, down to. And so we're probably not going to be able to get them to be closer than a distance of 1 from anything. And so epsilon equals 1 is a decent choice. Epsilon equals 1/2, that would work just as well. In fact, there are a lot of different values of epsilon that would work here. I'm going to sort of plead ignorance here and say, I don't really know what would work, but let's just stick a 1/2 in there and see if we can make it work, okay? Now, so this is a faithful beginning to a proof that there exists an epsilon greater than 0, right? That's a reasonable way to begin a proof that there is an epsilon greater than 0. And now we know how to continue the proof. We're trying to show that for the epsilon we've chosen, for all n something, and so we're just going to let n be anything, right? Anything at all. Now, this is like kind of unusual because like this might surprise you because when we're proving that a sequence does converge, then we're very carefully choosing the n. But that's because when we're trying to prove that a sequence does converge, then we're trying to prove there exists an n, and then it's our obligation to prove it. Here we're trying to prove for all n, so we just let n be a generic thing. Now, next we need to choose a value of cap n. So choose n in the naturals. So what am I going to choose it to be? Well, I don't exactly know what I need to choose it to be, but I'm going to choose it to be something blank, okay? I don't really know. I'm going to have to choose an n carefully, and then I'm going to have to get both of these things to be true, okay? So one thing I do know is I'm going to have to choose it greater than n, right? Because I'm trying to show that this is, so let's write down what our goals are for this n. We need to have a goal that it should be greater than cap n. And our other goal should be to make sure that the n satisfies this equation. So an minus L is going to be greater than or equal to epsilon. So if we think about the term an minus L, this an minus L can only be one of two values. Well, I mean, given the value of L, this can only be one of two values. It can either be 1 minus L in absolute values, or it can be -1 minus L in absolute values. So here, let's note absolute an minus L equals absolute 1 minus L if n is even, and it's going to be equal to -1 minus L if n is odd, because that's how the sequence an works. And what we're trying to show then is going to be that this has to be greater than or equal to epsilon. And we've already chosen epsilon. So let's fill in the value of epsilon here. It needs to be greater than or equal to 1/2. So under what condition? So the odd thing is we need to show that this is going to be greater than or equal to 1/2, but we don't yet know the value of L. How could we possibly know that this is greater than or equal to 1/2 without knowing the value of L? Well, it might seem that if we look at these, one of them might look like it's obviously greater than 1/2, and maybe it does, maybe it doesn't. If L is 0, for example, then this is going to be 1, and this is also going to be 1. If L is 2, for example, then this is going to be 1, but this one, that'll be 3. Positive 3, right, because of the absolute value signs. If L is equal to 3/4, then this will be 1/4, which is bad because it's not greater than 1/2. But if L is 3/4, then this one will be positive 1 3/4, which is certainly greater than 1/2. So it seems to depend here on the value of L, of course. And if L is a negative number, then we should be able to demonstrate that this is definitely going to be greater than 1/2. Because if L is negative, then this is 1 minus a negative, which is going to be greater than 1. So let's make a note of that. So note, so if L is negative, or let's say less than or equal to 0, then 1 minus L absolute is going to be greater than or equal to 1, which is certainly greater than 1/2, and we're going to be fine. And let's think about what happens if L is positive. If L is positive, then absolute 1, negative 1 minus L, this is going to be negative 1 minus L, which is going to be more negative than negative 1. This is going to be below negative 1, but then you take absolute value signs of it. That's going to be greater than or equal to 1, which is greater than 1/2. And so that's going to be fine too. So if L is non-negative, if L is positive in this case, then this one will exceed 1/2. And if L is negative, then this one will exceed 1/2. And so it seems like one way or another, we should be able to make sure that this works. So this helps us figure out how to choose n, right? If L is negative, then this is the kind of setup which will cause us to be able to prove that an minus L is greater than or equal to 1/2. So if L is negative, then we want to be in this case. And what do we need then? We need n to be even. So if L is negative, we need an even value of n. If L is positive, then we would like to reason about this case, in which case we need this to be -1, in which case we need n to be odd. And so this tells us how to choose n. So let's choose n. Let's choose n to be, we're going to choose it to be the next odd number after cap n if L is, now I'm getting confused, is positive. If L is greater than or equal to 0. So that we will get into the right case. And we're going to choose it to be the next even number after n if L is strictly less than 0. I could say less than or equal to, but then I would have a confusion about what happens when L is equal to 0. So let's see whether this choice works. So because it's the next odd or the next even, then it is certainly after L, and so we get n is greater than L. If n is if L is positive, then n is going to be odd. Oops. If L is positive, then n is going to be odd, and then we're going to end up in this case, and we're going to get an minus L is greater than or equal to 1/2, which is going to work. If L is negative, then n will end up being even, and then we'll be in this case, and 1 minus L will again be greater than 1/2. So in either case, we see that an minus L absolute is going to be greater than 1/2. And you can tell, I expect you can tell here that we could have chosen epsilon to be 3/4, perhaps even 1, and this would have worked just as well. So what have we demonstrated? Let's go over the proof structure given what we've gotten so far. So we have chosen an epsilon. We've let n be arbitrary. We've chosen a little n. And then we've proven eventually that little n is greater than n and an minus L is greater than 1/2. And so that's completely consistent with this required proof structure. There exists an epsilon such that for every little n, there exists a little n. We chose it so that this is true, we illustrated it, and this is true, we calculated it. So this is a demonstration that the sequence does not converge to L, And the only hard part here was that we didn't know what value of L it was, but that's good because we've proven that it doesn't converge to anything at all by this proof. And that's how we demonstrate that a sequence diverges.